Hello, everyone. I'm Qin Yubing from Renmin University of China. And the paper I'll be presenting today is titled Cognition-aware knowledge graph reasoning for explainable recommendations. And first, I'll introduce the background of this work. Knowledge graphs have been widely used in recommendation systems and have shown their powerful ability to help generate accurate and explainable recommendations. According to the ways of using knowledge graphs, knowledge graph-based methods can be classified into embedding-based recommendation methods and path-based recommendation methods. Here in this work, we focus on the path-based approach, which exploits the relational structure of knowledge graphs and provides interpretable recommendations for users. As for explainable recommendation, knowledge graph reasoning is an effective way to generate recommendations with corresponding explanations. For example, here is a reasoning path derived from knowledge graph reasoning. The item 2 is recommended to the user with the explanation. The user may purchase this item under the same brand as a previously purchased item. And in the past years, lots of knowledge-aware methods have been proposed for explainable recommendations. The problem of these methods is that most of them are logic-driven, and there's a gap between how algorithms and humans perceive the reasoning process. And to deal with this, in this paper, we get inspiration from dual process theory in cognitive science. And to imitate the reasoning process of human beings, we propose a knowledge graph reasoning model, COGR, for explainable recommendations. Dual process theory is a theory in cognitive science and suggests that human thinking involves two processes: an intuitive, implicit, unconscious, and fast process called system 1, and an analytic, explicit, conscious, and logical process called system 2. As specified in the theories, system 1 is employed to get an intuitive judgment of the current situation and reach an experience-based conclusion. System 2 is used for deeper and more logical reasoning to obtain more reasonable results. When humans make easy decisions, system 1 is unconsciously deployed for an intuitive judgment. And when complex reasoning is needed, system 2 is deployed and works interactively together with system 1. Inspired by dual process theory, here's the overall structure of our model. At each step during reasoning, system 1 is a relation-specific entity estimator for intuitive estimating. And system 2 is a reinforcement learning framework for explicit reasoning. System 1 generates the estimated vector of the next host entity and passes into system 2. System 2 uses this vector as a guidance, finds the reasonable entity in the knowledge graph, and feeds the entity back to system 1. These two modules interact with each other during reasoning until the final reasoning path is obtained. The red arrows in the figure indicate the workflow at the first reasoning step. And now I will introduce the two systems in detail. First is system 1, the entity estimator. For each relation, there is a corresponding entity estimator with a convolutional layer, a projection layer, and a relation-specific MLP, as illustrated in the left. The entity estimator can be summarized as the formulas in the right. The embedding of relation R and the embedding of the current entity are first reshaped and concatenated and fed into the convolutional layer, followed by a projection layer. The result vector is then concatenated with the user embedding and passes into a relation-specific MLP, which is phi R in the figure. The final output of the entity estimator is the estimated vector of the next hoop entity. Now I will introduce how to train System 1. The first step is to generate the personalized metapaths for every user based on their historical behaviors. Specifically, System 1 aggregates knowledge graph paths of all user item pairs under predefined metapaths and keeps the top K metapaths as the personalized metapaths according to their frequency. These personalized metapaths capture users' preferences so that the model is more likely to arrive at the items of user interest. Formally, a metapath is a sequence of relations and entity types within the knowledge graph path. Here are some examples of metapaths, and uses this metapath during reasoning. System 1 picks a path under some metapath from the personalized metapath, and then uses the relations and entities in the path to supervise the training of the entity estimators. As the formulas in the right shown, the training goal is to force the entity estimators to generate good entity vectors that correspond to the entities in the given path under some personalized metapath. The loss of System 1 is defined as the first formula. And here the P function calculates the similarity between the estimated vector and the actual entity embedding, defined as the second formula. And to simulate the System 2 in cognitive science, here in our model, System 2 is designed to conduct logical and explicit reasoning under the guidance of signals from System 1. We use a reinforcement learning framework to implement System 2. Assume that the current step is the Tth step. Then the current state is defined as the concatenation of user embedding, the type embedding of user entity, the embedding of the current entity, the type embedding of the current entity, and the estimated vector of next hoop entity. And the action is defined as the tuple of the next hoop relation and next hoop entity. A terminal reward is employed, which means the reward value depends only on the terminal entity. And the training goal is to maximize the expected cumulative reward. And the policy gradient is defined as follows, where theta means the trainable parameters of System 2. And the pi function denotes the policy network, and v function denotes the value network. We perform experiments on 3 categories of the Amazon e-commerce datasets, including beauty, cell phones, and clothing. The results show that our model outperforms baselines on 3 datasets under all metrics, and this verifies the effectiveness of our model as a whole. We also conduct an ablation study to observe the effectiveness of the 2 systems separately. The results show that removing any of the 2 systems leads to a decline in recognition performance. This indicates that System 1 and System 2 both contribute to the final performance of the proposed model. To study the effects of the personalized metapaths, we evaluate our model with and without personalized metapaths. The results are in the left table. We notice that Cogger outperforms Cogger RM on both datasets. This shows that personalized metapaths filters out the less helpful metapaths for different users. And we also yield the distribution of users over different metapaths shown in the right figure. We notice that distribution of users over different metapaths are different. Hence, considering personalized metapaths is necessary during reasoning. Besides, we evaluate our model with and without type embeddings on 2 datasets. We also use type embeddings with different dimensions to explore how the dimension influences the model performance. And the results show that on both datasets, Cogger with type embeddings outperforms Cogger without type embeddings. Besides, as the dimension of type embeddings increases, there is a declining tendency of the recommendation performance of our model. We also studied how the size of action space influences the model performance. We noticed that the model performance declines as the size of action space increases. One possible explanation is that the action pruning strategy effectively filters out irrelevant actions in the full action space. Promising actions are kept and selected with higher probability, hence better performance is achieved. And in conclusion, in this paper, we get inspired from dual process theory and propose a knowledge graph reasoning method, COGR, for explainable recommendation. And the model consists of an intuitive estimating module, system 1, and an explicit reasoning model, system 2. And these two systems interactively work for the final performance. Experiment results verify the effectiveness and the interpretability of our model. And that's all about this paper. Thank you for listening.